Hi, my name's Steven, and today I'm going to be talking to you guys about the resonance stabilization energy of benzene. So first I'm going to introduce you to benzene and talk a little bit about it. So what is benzene? Benzene is a cyclic hydrocarbon consisting of 6 carbon and 6 hydrogen atoms. And this is shown all the way to the bottom right. In comparison, cyclohexane also is a cyclic hydrocarbon with 6 carbons, but this compound has 12 hydrogen atoms and is formed mainly of single bonds. So what makes the benzene special? It's foundational in many organic reactions, and it's used across industrial and research fields alike for creating anything from rubbers and plastics to pharmaceutical compounds. The conjugation brought on by the sp2 hybridization throughout the benzene allows for a more stabilized hydrocarbon compared to the cyclohexane. So how can we determine this energy stabilization received through the resonance? Now, performing experiments with benzene first off is dangerous because it's high in acute toxicity, and it's highly flammable. So this is something that is very important for us to analyze in benzene, but at being smart chemists, it might not be as beneficial for us to actually use benzene in our experiments because of these dangers. So how can we do this without putting ourselves in harm's way? So to determine this resonance energy of benzene, we're going to use calorimetry. Calorimetric techniques allow us to determine the internal energy of a given system. This internal energy is equal to the total heat released in the system when it's at constant volume. The thermodynamic data that we can collect through calorimetry can allow us to determine the resonance energy of benzene. And this is analyzed through a theoretical isodesmic reaction shown at the bottom left. Now, what's interesting to note about this, which is basically the definition of an isodesmic reaction, is that benzene is made out of 3 double bonds and 3 single bonds, without including the bonds with the hydrogens, whereas cyclohexane is made out of 6 single bonds. Now, if we were to theoretically react these two into this compound on the right, CDDT, this CDDT molecule has a total of 9 single bonds and 3 double bonds. And these bonds total up to the amount of bonds found within benzene and cyclohexane. So that's basically the definition of what an isodesmic reaction is. And using this theoretical reaction between benzene and cyclohexane, we can then further analyze the thermodynamic characteristics of cyclohexane and CDDT to ultimately determine that resonance energy of benzene. Now for that theoretical isodesmic reaction defined before, the following Hess cycle is utilized. So the first 3 values were determined through literature review, and this includes the enthalpy of condensation of benzene, the enthalpy of combustion of benzene, and the enthalpy of condensation of cyclohexane. Now, what's interesting is that basically the enthalpy of condensation of both benzene and cyclohexane are analogous to the negative enthalpic difference of vaporization between the 2 molecules. And this is just basically in relation to the reverse reaction. But these 3 values were determined through literature review, and these values are found at the bottom. The following 2, the enthalpy of condensation of, the enthalpy of combustion of cyclohexane and the enthalpy of combustion of CDDT, were determined experimentally throughout this presentation, and they were determined through calorimetry as mentioned before. And the last value, the enthalpy of vaporization of CDDT, was calculated using known data of the vapor pressure of CDDT at certain temperatures. So shown here is the calorimetric data for cyclohexane and CDDT. So like I had mentioned before, the internal energy of the system is equal to the total heat released in the system. This is because the system is at constant volume within the calorimeter. And after we determine these internal energies, subsequently, the change in enthalpy of the reaction is calculated. Now, what's not noted on this slide is that when you're actually doing the cyclohexane combustion reaction within the calorimeter, cyclohexane is loaded within a gel capsule. And when you do this combustion reaction, the gel capsule also releases heat in a combustion reaction. So that also attributes an addition into the internal energy as well, or as added on with the cyclohexane. So because we already know the specific heat of the gel capsule, by determining how much of the gel capsule combusted throughout the reaction, we can determine how much of the internal energy can be attributed to cyclohexane by itself by subtracting the amount of heat released by the combustion of the gel capsule. Now, the change in enthalpy of vaporization of CDDT, this value was shown in the previous slide in the table, but I'm going to go a little bit more in depth in it right now. So we had known values of basically the vapor pressure of CDDT, this molecule, at different temperatures. Now, when these are plotted regularly, you do not get an easily analyzed graph. So if you were to take the natural log of the pressure and the inverse of the temperature and plot these, you get this very linear relationship. Now, once we have this linear relationship, we can follow the calculations on the left, and we can ultimately determine the change in enthalpy of vaporization of CDDT. And we determined that it was 47.671 kilojoules per mole. So now I'm going to go a little bit more in depth on some of the calculations that I mentioned previously. So first I'm going to talk about that change in internal energy for combustion. So for the example for both of these, actually, I'm going to be talking about the CDDT molecule in the trial 1. Now, these trials were actually performed in different calorimeters. One of these calorimeters was dotted, one of them was non-dotted. And these calorimeters both had different specific heat capacities, but we knew them prior to this experiment, so that made a lot of these calculations very easy. So first we determined the change in temperature of the system, and we did that by basically constantly measuring the temperature throughout the system as the reaction proceeded. So we got an initial temperature and a final maximum temperature, and that allowed us to get this change in temperature. Now, the change in internal combustion energy is equal to basically the specific heat, the negative specific heat of the calorimeter multiplied by this change in temperature. And ultimately for the CDDT trial 1, we ended up with 49.204 kilojoules. And for samples utilizing the capsule, like I had mentioned before, the heat of combustion of the capsules, heat released, was subtracted from the determined change in internal energy of combustion for those cyclohexane reactions. Now talking about the change in enthalpy for combustion. So like I had said, we're going to be talking about this through CDDT trial 1. And first we need to determine the change in moles of gas throughout the sample. So basically we were able to take the mass of the sample and divide that by the molar mass. And this would ultimately give us our moles. Just a little bit of stoichiometry. So now we're going to look at this change in enthalpy of combustion reaction, and this is equal to the change in internal energy of combustion plus the moles multiplied by a gas constant multiplied by the maximum temperature. So if we were to plug all these numbers in, it's also important to note that the temperature in this case is in Kelvin because the gas constant is also in Kelvin, and the gas constant was also adjusted to be in kilojoules for simplification of calculations. We end up with negative 49.188 kilojoules, but because the change in enthalpy is basically very dependent on the amount of moles, we divide this number by the molar mass, or I'm sorry, the moles of gas that we had calculated prior, and we get 7,697.653 kilojoules per mole for the change in enthalpy for combustion of CDT trial 1. And these calculations were performed identically for each different trial for each sample. So now I'm going to be talking about the actual resonance energy of benzene. So basically, I had already talked about this prior. The first 3 values, the enthalpy of vaporization of benzene, the enthalpy of combustion of benzene, and the negative enthalpy of vaporization of cyclohexane were all determined through literature review. Now, the enthalpy of combustion of cyclohexane and the enthalpy of combustion of CDDT were determined through the calorimetric data that I had shown before, and the change in enthalpy of vaporization for CDDT was determined through known data. Now, using Hess's law, we can basically add all of these values to determine the negative energy of resonance of benzene. And this is just due to the way that the overall reaction is set up. Now, when we plug all these numbers in, we get a negative E resonance of negative 141.763 kilojoules per mole. But that's kind of pointless to us because we'd rather have the positive energy of resonance. So we get 141.763 kilojoules per mole, and this equates out to about 33.882 kilocalories per mole. Now I converted this to kilocalories per mole because a lot of different literature review and sources on the internet tell us this value, which has already been reported in the units of kilocalories per mole, and it's been reported that, this value is close to the determined data, anywhere ranging from mid 34 kilocalories per mole all the way up to 36 kilocalories per mole. So we're just below that range, and this may have to do with one error, or not one error, but one thing omitted from this presentation, which is basically the inclusion of the heat release of the combustion of the actual ignition wire within the calorimetric system. Now in the calorimetric system, in this bomb calorimeter, you have this ignition wire, and basically you know the specific heat of this ignition wire, and when you ignite the system, a certain part of the ignition wire basically burns up and releases heat. So if you know the amount, or like the amount of the wire that had been burned up and released heat, and you know the specific heat, you can determine how much heat was released due to that ignition wire. And that was omitted from this experiment, so that could potentially explain our differences in values. But overall, we still had a fairly close value for our energy of resonance of benzene. So briefly, why is the resonance energy of benzene relatively large? And I say relatively large when just comparing it to other basically conjugated hydrocarbons. So the delocalization of the electrons in the aromatic system obtain larger stabilization effects. So basically in all of these other compounds, most notably I'm going to be talking about this cyclooctatriene, is the way that they're oriented. They're not aromatic, so they're not completely linear. So the way that the sp2 orbitals orient themselves, they're not really in like a direct line with each other. So the conjugation is not as relevant. So it doesn't add as much of a stabilization. It does add a stabilization effect, but not as large as benzene. Benzene is aromatic. All of the sp2p orbitals, all of those sp2 hybridized orbitals are in line with each other. And that allows for that delocalization throughout the benzene, which attributes to its relatively large stabilization resonance energy. So briefly, I'm going to talk about a little bit of other research that's been done in this field. So in 2004, Jenkins and Tall reported on the quantum pathways of resonance energy transfer. Now, a lot of the information in this paper was both hard to read or inaccessible due to the University of Pittsburgh's rights and privileges within reading this journal. I don't think we really have access to much of the data inside this journal. But just by reading the abstract, it seems very complex in a lot of fields that many of us be very interested in. Not interested in, but might not have the knowledge on. So basically the report that although we can, after reading this abstract, we can determine that although the resonance energies may seem like an elementary topic at this point, we're just measuring some fairly simple thermodynamic data through calorimetry. Even as we further our knowledge into the new fields of chemistry, such as quantum chemistry, we figure out that we have so much more to learn about these systems than we had previously thought. And this can be applied to so many different fields in chemistry. And just as we learn more, especially in quantum chemistry, we can reevaluate things that we had thought to be simple prior, and we can begin to understand them on a completely different level that we never had before. So that wraps up my presentation. These are the sources that I used. The first three were the literature review for the values that I had mentioned previously, and the last one is for that last paper that I had talked about the quantum pathways for resonance energy transfer in benzene. And I'd also like to point out that A lot of the data and calculations and stuff, a lot of that was attributed to the lab manual for physical chemistry at the University of Pittsburgh. And that is my talk. So everybody, thank you for watching.